part of it, as I said, where I stopped the last time. Okay, we said that in general way, let's say to get what we call to uh, express the principle of momentum, we say that the external forces for time t1 minus t0, that is means is the integral of the forces um, during traveling of the particle. It's from t1 to t0. This is the initial state, and here the actual time or state. Okay, if the forces is constant, let's say we integrate within the interval of time between the actual and the initial state, and this is should be equal to, for the mass, in the case of the mass or the particle mass point is time dependent. In this case, we have the difference between the momentum, let's say m1 v1. M1 is the mass at time t1 multiplied by the velocity at this time minus m0, which was it's the mass of the particle at time t0, the initial state, multiplied by the velocity at the initial state. This is the case when the mass m it's changing with time. In the case of the mass which is constant, in this case that we have only the mass multiplied by the difference between the actual velocity and the initial velocity. Then we have seen some particular case when there is no external forces. This is, we call it the principle of conservation of momentum. Okay, that it means the momentum at time t1 is equal to the momentum at time t0. Okay, there is no change in the momentum. That we said what is important, that provide by the simple way the final velocity at time t1, this principle, principle of momentum, but do not provide acceleration or equation of motion. Okay, is used that advantages when the force variation is difficult to determine or unknown. There is the interaction force is the force in the system, which is the action equal to the reaction. That we said that here, if we have to apply the momentum, we should apply it, in different direction. If we have coordinate system x, y, then we should apply the momentum in y direction and the momentum in x direction. That it means we look to the force, the component of the force F of the vector force in x and in y with the composite, and the same for the velocity in x and y direction. And we look to the momentum. We say that the component is bx, the momentum in x direction is only the mass multiplied by the velocity in x direction, and the same for the case of in y direction. There is two cases. It can happen that the momentum is positive or negative. That is means if there is in x direction, the velocity is in positive x direction. in this case that we have the momentum which is positive. But in the case of the velocity is opposite to x direction, in this case we have the momentum Bx which is minus mvx. Okay, now we said here in the case of the mass which is constant, only to make the integral from the time t0 to the actual time of the force in x direction, then it's equal to the mass which is constant here, the difference between the actual velocity and the initial velocity. Okay, but in x direction. The same principle we use it also in y direction. And that is the case when you have acceleration and deceleration with constant force. Okay, then in this case we have t equal to t0 at time, initial time. We have f which is constant. We have the particle with the mass m and the velocity v0. After this, there is the acceleration. That is means that we have here at the actual time v1. Okay, then we have there is acceleration. That is means the forces, yeah, will be the integral of the forces. The first term here, it's the force which is constant multiplied by the difference between the actual and the initial time. Now, if we look for the here positive change in velocity when there is acceleration, but if there is deceleration, that is means f. Okay, you have the motion in this direction along x direction in positive x direction. Okay, this is the initial state here, the actual state. Now the forces is opposite to the direction of the motion. Okay, in this case we have only to make the with minus f, and we have here opposite to the previous equation minus f, which is multiplied by the time, multiplied by the time, the difference between the actual time and the initial time, and this is will be negative. Okay, in this case, that is there is deceleration. Then we said a negative change in momentum. That is means we have m multiplied by v1 minus v0. This is negative. Why? This is f is constant. Time, the difference between the actual time and the initial time should be positive. Then in this case, the first term is negative. Then it means here what we have the velocity v1, the actual velocity is smaller than the initial velocity. Then negative change in velocity means there is deceleration, there is no acceleration. Okay, we can determine then after this velocity at time t1 from this expression here. It's given by the following. Okay, velocity will vanish as here if t1 minus t0 it's equal to m multiplied by v0 divided by f. Okay, and then in this case that we said the velocity will vanish as we are doing the deceleration. Okay, then it means certain times there will be velocity will reach the value 0. Okay, we consider now to show this principle. Okay, we consider now the particle A here, which has the mass MA. There is here the particle, second particle MA. The particle MA has the initial velocity VA0, okay? The particle B has the velocity VB0, yeah? Then we say that are moving across a frictionless surface with a constant velocity, okay? Then it means what we have here, we have the motion, it's along x direction, where we have here the velocity x dot. There is no friction, it means there is only the contact force, N, yeah, between the masses and the ground, and between the mass here, in this case, we have spring, which is pretension, it means that we compress the spring, yeah, and we attach the two masses, yeah, by connector here. Okay. Then what we look at times t0, the initial state, the connection is released. That means we remove now this connector here between the two masses, yeah, and we let the mass MA, MB, and the spring, yeah, free. Then in this case, when we let them, there will be clear, yeah, the mass MA will change the velocity FV. It will become VE1. The same for the mass MB. The mass for the point B or the particle B will be VB1. Okay. What we do the cut here to see the spring force. This spring force here, we call it FT. Okay. And should be here for the mass 1 MA, it's interaction. For the mass MB, it's in compression. Okay. Then we have here the relation is valid action, it's equal to reaction. Why? Because when we cut here, there is a force in this case in actual interaction, and there is the force here in compression. That means when we make the sum of the forces here should be equal to 0. Okay. Now, if we look to the principal momentum of three masses, we take the mass alone, MA, and also the mass MB. Okay. Then we integrate the force here with respect to the time, T1 actual time and T0 the initial time, and we have which must be equal to the mass MA multiplied by the actual velocity at time T1 minus the same mass multiplied by the velocity at time T0. The same principle will be applied for the mass, the particle, yeah, or mass point MB. In this case, we said that F it's a negative, Y it's opposite to X direction. Okay. Then we have here the same principle, the second term of the momentum, the difference between the two momentum, MB, VB1. This is for the time T1, and here the time T0. Then if we make now the sum of the two terms here, for the right hand term, there will be 0, as it's positive here, the same force. Spring force here is the same. Then in this case, we have here plus F minus F. This gives 0. And we make here the difference between this right hand terms. We have MAVE1 plus MBVB1 minus MAVE0 plus MBVB0. And this is, you can see that its width here is equal only to the mass MA plus MB, yeah, equal multiplied by V0. That it means here VE0 and VB0, yeah, are equal as they are attached together with the connector. Okay, this is, we can simplify VE0, VB0 is equal only to V0. Now we can resume that to say the momentum of the entire system remain constant if there is no external forces acting on during some interval of time. Okay, this is what we call the conservation of momentum. The center of mass of the entire system does not change its velocity. As we have here two masses, okay, if we say the spring is massless, the connector is massless, okay, there will be the center of mass somewhere between the mass MA and MB. It will be somewhere between the two, okay? It depends if MB is greater than MA or MA is greater than MB, but it will be on this line. Now, if we want to look to the location of center of mass, okay, how to find it? We know the center of mass of the particle MA, okay, we call it SA. This is only, as we said, this is where we see letter, yeah, for it will be more clear, let's say, to define it exactly where is it, yeah, when we see the rigid bodies. But for the masses, center of mass, the center will stay, yeah, on the mass point itself as it's very small. This is, we call it SA. Here there is SB, okay, the center of mass for the particle MB. And now the center of mass of the whole system, yeah, let's say MB and MA, it will be somewhere here as. How to determine it? We say that the position XS, that it means the distance here to S, we have to define it only by the mass MA multiplied by XA, that is means the mass MA multiplied by the position of the point or the point mass MA plus MB, which is here the particle, the mass point MB, multiplied by the position of this mass B here, divided by the sum of the two masses. Then we can get here now the position of the center of mass of the whole system. We express it by XS, okay? And now we can say that here MA plus MB multiplied by XS, which is here the position, it's only MAXA plus MBXB, okay? Then we have here, when we make the time derivation of it, this is the position, okay, of the center of mass. If we make the time derivation, we will get the velocity, Vs, and we assume MA and MB are time independent. Then in this case, we stay with MA plus MB, and this is here, we get MA velocity A plus MB velocity BB. Yeah, this case is only alternative formulation of the momentum of the entire system, okay, with the center of mass instead to use the momentum, the conservation of the momentum. Then we express that here momentum of the entire system is equal to total mass times the velocity of center of mass. That is means here we have the sum of the mass of the two masses multiplied by the velocity of the center of mass. This should be constant. Okay, this is it's only valid when we have m is constant and the velocity is constant. Now we come to the impact, the case of the impact when there is the impact between two particles. It can happen also to have it between two rigid bodies, like you have the impact between two cars, okay, or let's say trains or any mechanical system. This is, we can say, the impact occur when two bodies collide with each other during a very short period. Okay, the impact can happen, but the duration time of this impact is very small. Yeah, causing a relative large impulsive force to be exerted between the two bodies. Now we use this application. We apply the principle of momentum. Okay, we say two particles immediately before and after the impact. We look what happens before the impact and after the impact. The impact is somewhere here. Okay, but the impact, as I said, is very short. Then we say that here, for example, you have the two, we take two masses, MA and B. The mass MA has velocity V 0. The mass MB has velocity VB 0. Okay. And now okay, I have a message that it's there is better quality of internet. Okay, it seems that it's okay. I'll return back to the slide. Yeah, we said that immediately before the impact, we take the time t equal to 0. Immediately after the impact, time is equal to t1. Okay, that keep in mind that during the impact is very short. It's clear during the impact the forces between the two bodies will be, let's say, high. We take here in this case condition for the impact. VE0 is directed to the right positive and greater in magnitude than VB0. Okay, if VE0 is smaller than VB0, there will be no impact. Okay, if they are equal, the two velocity are equal. In this case, yeah, there will be also no impact. The impacts can happen only when you have VE0 it's greater than VB0. Yeah, then it means this mass MA will collide the mass MB. Then here, or there is a second case when you have VB0 is directed to the left, negative. That is means like you have the car traveling in this direction, okay, and the car, let's say, with the mass MB, it's in opposite direction, then there will be the impact. Then if we take the free body diagram, that just means we cut, okay, between the two masses after the due to the impact, then we will get here the forces due to the impact is only F at time t, okay, between the two masses, and it's very high. As you see, the maximum reached somewhere here. Now, if we take the principle of momentum for the masses, if we take here now the masses ME, yeah, it will be negative as F is opposite to the direction of the motion. Then we have the difference between the two momentum. We apply the same for the forces MB, okay? And we have F is positive. Then we have the differences, the difference between the two masses. Then, in the same as we have done it previously with the connector between the two masses, we will get here ma multiplied by velocity of the mass ma at time t1 plus mb multiplied by the velocity at time t1 will be equal to the mass ma multiplied by the velocity of the mass a at time t0 plus mb multiplied by the velocity uh, of the mass b at time t0. Then we said the momentum of the intersystem remains constant if there is no external forces acting on during some interval of time. There is the problem of this one is there is only one equation for both velocity. Okay, if we know the velocity, initial velocity v is 0, and we know the velocity of the mass mb vb0 after the impact, okay, the two velocity will be unknown. There are two velocity here, but only one equation. Then in this case, what we introduce what we call the coefficient of restitution. We note it by the term epsilon, okay? We define it as the ratio, negative ratio between the difference between the two velocity at time t1, yeah, and the difference between the two velocity at time t0. Then it means there is the second equation now between the two velocity. Then we have VB1 will be VE1 at time t1 plus this coefficient of restitution multiplied by the difference between the two velocity at time t0. Then we say that here the coefficient of restitution is only the ratio of the relative velocity after and before the impact. There is two cases, yeah, let's say two extreme cases. When epsilon is equal to 0, then in this case both velocity are equal, yeah, the relative velocity is equal to 0. This is, we call it plastic, or we call it also inelastic impact. Okay, we will see the difference between the two. Epsilon is equal to 1, the relative velocity remains the same. Yeah, then it means if it's equal to 1 here, yeah, you have this velocity will be, yeah, equal to this one. Then in this case, there is, we call it elastic impact. Okay. If we insert the expression of epsilon, okay, or let's say here the expression of epsilon, that it means we take VB1, yeah, we express it as function of this term, the coefficient of restitution epsilon. Then in this case, if we replace by epsilon, yeah, we can find VE1. Yeah, only we replace MB1 here by this expression here. Okay, when we replace it, we develop, we get now the expression of EV1. As we know V is 0 initial velocity of the mass MA, we know the initial velocity of the mass MB, yeah, we know the masses MB and MA. Now we have should know the term of this coefficient of restitution epsilon. Okay. Then we get, now when we get VA, we can use the first equation here. We will get VB. Or we can replace it here. We will get also VB. Yeah. Then it means we have now to solve such a problem, let's say contact problem, yeah, or the impact problem. We have now two unknowns and two equations. Okay. Then we have here for VB, as we said, we can replace it, yeah, in either first or second equations. And then we get also the same for VB1. Yeah, we will get VB, it's as function of B0, which is known, epsilon, MA, and VA0. Now coming to this coefficient, okay, we call it coefficient of restitution, this one. We take the case of perfectly elastic impact on the wall. Yeah, perfectly elastic, we said that in this case, by definition, perfectly elastic means that we have epsilon is equal to 1. Okay. Then we have here the wall. Okay. The wall, we assume, or let's say, we imagine that its mass, it's infinite. Okay. And the velocity of the wall, as it's fixed, yeah, its velocity will be equal to 0. Okay. We take now the particle MA, which moves to the wall, yeah, with the velocity 5 meter per second. Now apply only the coefficient of restitution and not the principle of momentum. If we apply now this relation here, yeah, of the coefficient of restitution, in this case, if we apply it, what we have? We have VE0, okay, it's 5 meter per second. VB1 and VB0 are equal to 0, as it's the velocity of the second body, which is the wall, okay. And now we have here epsilon. It's only when we replace here, we will get the ratio between the actual velocity VE1 and VE0. Then it means we see that in the case of perfectly elastic impact, the initial velocity and the final velocity, yeah, are equal in absolute value. Yeah, the difference is only that VE1 is negative. Okay, it's now opposite direction. And we said that here for perfectly elastic impact, one have also epsilon is equal to 1. Yeah, this is, we said it before. Now, perfectly plastic impact. Now the second extreme case. Yeah, on a wall. We said also that here the masses MB, yeah, of the wall is equal to 0, is equal to infinity. The velocity, its velocity is equal to 0. The same here for the velocity after the impact. Okay, the mass also will stay infinite. Now we take the same velocity as in the previous example, which is 5 meters per second. We said for the perfectly plastic impact, epsilon should be equal to 0. Okay. Now the particle has this initial velocity. Okay, the particle A. The wall, yeah, has the velocity before the impact and after the impact is equal to zero as it's fixed. After the impact, the body have the same velocity. Okay, yeah. PE1 is equal to zero. In this case, the body will hang on the wall. Then in this case here, we'll see in the expression here, okay, VB1 and VE1, yeah, the difference will be equal to zero. This is here, yeah, if the difference is equal to zero here, epsilon should be also equal to zero. Then it means for perfectly impact, one have also epsilon is equal to zero. Now, between the two cases, elastic impact and plastic impact, there is what we call partially elastic impact on the wall. Then if we apply the same here, the coefficient of restitution instead to apply the principle of momentum, we have the same conditions for the wall. Okay, we take same mass with the same velocity, initial velocity, and we look now after the impact, the the velocity of the mass ma will change the direction, yeah, with the velocity to 0.5 meter per second. Then we said in general one have for partially elastic impact the coefficient of restitution. In this case, epsilon is between 0 and 1. 0 correspond to the plastic impact, 1 to the perfect elastic impact. Okay, this is the value what we have from here. Particle initial velocity is 5 meters per second. The wall, its velocity before and after the impact is equal to 0. Now a part of the energy is lost through deformation. VE1 in magnetism is less than VE0. Then, for example, for VE1 is equal to minus 2.5 meter per second, we will get the coefficient epsilon is equal to the height. Now we take the perfectly elastic impact of two masses, that is means epsilon is equal to 1 if we apply the coefficient of restitution and principle of momentum. Now both methods. We have here just before the impact, we have MA has 5 meter per second the velocity. MB, its velocity is 2 meters per second. That it means following in the same direction, okay? And in the same way, let's say ME will collide MB, yeah? We look now just after the impact, yeah, short after. We imagine that here MA we will get 1 meter per second and MB will have 4 meter per second. Then in this case, if we apply the formulation of the coefficient of restitution, in this case, we will get epsilon is equal to 1 as we have perfectly elastic impact. If we replace in this equation, we will get VB1 will be equal to VE1 plus the difference between VE0 minus VB0. Okay, the one here, it's only epsilon. Okay, then if we replace now, knowing the initial velocity, and we know the velocity after the impact of the mass ma, yeah, we will get here the velocity of the mass mb, which is 4 meters per second. Now we take the case of ideal plastic impact of the two masses. That is means in this case, if we apply the equation for the definition of coefficient of restitution, yeah, in this case that we have epsilon, which is equal to 0, yeah, which is the opposite case for the perfectly elastic impact. We take the same initial condition just before the impact. We have 5 meters per second for MA, 2 meters per second for MB, and we have just after the impact, yeah, then here the initial speed, final speed after the impact are the same, yeah, as they are now connected, yeah, or hang together. For plastic impact, one have in general epsilon is equal to 0. Okay. Now we take the case of the oblique impact. Direction of the impact force Ft does not coincide with the direction of the velocity before and after collision. Then it means here we have the case of MB, which has VB0, yeah, traveling or moving along this direction here, okay, and we have the mass ma, which has the velocity, initial velocity ve0, which moves along this direction here. We take the coordinate system, let's say et tangential and normal. For the case the oblique impact on a wall, okay, we have ve0 here in this direction, yeah. After the impact, we'll change the direction, yeah, and it will get the velocity ve1. And of course, the angle changes here, alpha, before and after the impact. Then we have here the relationship. That is means if we look to this, we can have the velocity ve1 after the impact can be decomposed into two components, tangential one and normal one along this two, projected along this two axes. Okay, the same principle we do it here for the initial velocity. Now we say here distinction between the normal and tangential direction. In normal direction, the previous relation are valid. That's the coefficient of restitution in normal direction. Epsilon will be, yeah, always defined by the following relation. Now taking perpendicular to the normal impact, which is the tangential direction, that is means along this direction here, yeah, the tangential one. There is motion depends on whether the contact surface are smooth or frictions occur. Yeah. Smooth contact surface, no force in tangential direction. That is means in this case, the velocity tangential after the impact will be equal to the velocity initial the velocity of the mass A before the impact. The same for the particle VB, the particle MB. Okay. In the case of perfectly elastic, frictionless, oblique impact on a mole, epsilon is equal to 1. In this case, we will get the velocity after the impact will be equal to the velocity before the impact for the normal component. Okay, the same will happen for the tangential component. Then it means there is constant speed and the angle of incidence, which is equal to angle of reflection. I will stop here now. Okay.